All right, good morning, everybody, and welcome. Because I'm part of a big corporation, I have to start with this. The lawyers always come at me and say, please don't make any lawyer jokes. Then this is the material they give me. I mean, at some point, you got to help yourself, right? So I actually also want to start with this. We've had a lot of conversations about the RISC-V ecosystem, and it's been extraordinary over the past year to see the ecosystem grow, and you're seeing a variety of different numbers, and we're very excited. In fact, one of the core reasons why Western Digital went public with its intent to transition 1 billion cores a year to RISC-V was so that we could encourage ecosystem growth. We wanted to send a strong message to the ecosystem that, hey, this is for real, this is ready for prime time. You can join this ecosystem and good things will happen. So the ecosystem has grown very well. Now, if I had sort of some wishes, sort of what's next, a couple of things come out. One is that a lot of the ecosystem growth has occurred on the hardware side. And we'd like to see a little bit more on the software side. So encourage all of your friends, write lots of code, and I'll give you an example of that in a second. The second thing is that we'd like to have more people speak loudly about their intent and their plans to use RISC-V. I would love to be in a situation where at, let's say, next year's RISC-V Summit, we submit and say, hey, we'd like to do a keynote speech, and they say, hey, we have way too many and far more interesting people wanting to talk about RISC-V. You get no time slot. That would be like a super big win for me. Okay? Now, to give you now everybody can contribute to the ecosystem. So I'll give you a concrete example, and I'll give you the software example. So one of my favorite software tools that I use all the time is something called Platform.io. And I think the team is here from Platform.io. It's a build tool for embedded development. And so one of the things I did is I actually spent a weekend doing a 12-video screencast tutorial using Visual Studio Code, Platform.io, the Sci5 Hi5 board, and walk you through how to write RISC-V assembly language code. So it's a beginner's tutorial on how to write RISC-V assembly, all wrapped inside callable from C code. And this is a 12-video series, and you should watch social media. We'll try to make those videos available. But those are just examples of things that any of us can do in order to contribute to the overall ecosystem. And just because I can't resist the other lawyer joke, the reason the videos haven't been posted is because I'm using the Visual Studio Code logo in the videos, and we have to get permission from Microsoft before we can post the videos. So that's my second lawyer joke for the day. I said I wouldn't do any, and I'm already up to 2. So there you go. All right, so I'm going to actually go through 3 things today. I'm going to go through a little bit of a review of why is Western Digital doing this? Why is a storage company so invested in and interested in processing, and give you how we think about data? And that's kind of where this starts. And then I want to go through 3 announcements of things that Western Digital is doing. And the interesting thing, and one of the things I want to keep top of mind, is that none of my announcements are going to be product announcements. And when we preview some of our work with press and industry analysts and things like that, I often had to reiterate that everything I am going to talk about today, none of it is a product announcement. So just keep that top of mind. So let me start here, which is how we think about data. You can think about this in very complicated terms, and I love that we had a team that essentially said, let's simplify this and put all of the data into 2 camps. And sure, you can have all sorts of arguments about different types of data, but thinking about it in terms of big data, the things that you amass for scale, the things that we've been doing for the past decade, things that you associate with, let's say, a Hadoop type of workload, we call those big data. And then on the other side, and where we've seen a lot of activity in the recent past here, is that we think about more the immediacy of data, where we need to operate on data and get results right away. And the easy example to think of is the autonomous car that needs to make decisions on the spot. They can't take all of the data they collect, send it to the cloud, and hope they get an answer before the next car comes along and causes a crash. And so we basically we think about data in these two constructs, one focused on scale and one focused on performance. And yes, there's a continuum, obviously, between those two. And so the reality is that we see this notion of the data going from the core to the edge, and the core being more sort of focused around the big data construct, and the edge being more focused on the fast data construct. And so the reason why we see RISC-V as so interesting is that when we think about this paradigm, we think about the fact that the architecture of processing that has served us so well for, let's call it, the last 40 years, really doesn't necessarily suit us as well for this next degree of architecture. And that's why we were thinking we need something new. We need to have the ability to think about processing data close to the edge, and we need to bring the processing to the data, where we've spent the last 40 years shipping data to the processor. So processing is very, very important. But for us, processing is a means to an end. It is not the end unto itself. We don't believe that the workloads of the future are where you have the processor at the center of the universe. We believe data, the customer's data, your data, should be the center of the universe. And so this really is, in effect, the money slide. We've spent this multiple decades with general purpose processor architectures. And those served us well. We cranked the clock speed for a few decades, and that continued to serve, and then we went multi-core and that kind of. But then when we started looking at this core-to-edge construct, we said we can't turn that clock anymore. We can't just keep adding cores. We now need to think about workloads in a very specialized way. And so while general purpose processors are not going to go away, they're not going to stop being used or anything like that, we think there's an increasing number of workloads that are going to need what Krista called diversity, where we can focus in on specific workloads. And guess what? You're already seeing it. Whether it's people using GPUs in order to solve machine learning, whether it's people creating FPGAs because they want to optimize a particular algorithm, or a TPU from our friends at Google. And I think it was last week, Amazon announcing their own processors because the general purpose world is not meeting the needs of some of those requirements. So that's how we think about the data. Now, we've been at this for a while. So we started this back in 2014. We started to notice a couple of things. Not only was the general purpose world problematic for the next generation of workloads, the general purpose processor vendors were heading down a path of locking down interfaces. And when people ask me, what's my 10-second answer to why is Western Digital doing this, it's because we believe the world needs open interfaces. Open memory buses, open coherency fabrics, open I/O buses, and the like. And so we think that that openness is what will enable that next generation of innovation for these new architectures. And so very rapidly, the team at Western Digital saw, let's join the foundation as a founding member, platinum founding member, and continue to do some of that early work that you heard Chris and Rick talk about. And then last year, we announced that we will transition all of our devices to RISC-V over time. And this does take quite a bit of time. Anybody who's done silicon knows that this stuff doesn't happen overnight. But Western Digital as a company today ships about 1 billion cores a year. And we're, as we sort of do our fast forward fetch, we see that we're getting to doubling that to 2 billion cores a year in the not too distant future. And so we've continued through 2018 to make contributions to the RISC-V ecosystem. You see some examples here where we contribute to Fedora Linux. So we now have a full Fedora Linux implementation that runs on RISC-V. And also, our team in Israel did the Arduino port so that if you're doing some of that embedded work, you can use the Arduino libraries to help you do that work. And then today, you're going to hear about our next set of announcements to contribute to RISC-V. As I said, the core thing and the reasons why we're doing this is because we need this openness. We need these open interfaces so that we can attach anything in any which way in which we want to at the cost levels that make sense for a particular application. And what Chris had called diversity can also be called configurability. The ability to build special purpose for a particular workload, because cranking the clock speed is just not going to cut it anymore. All right, so for announcement number 1. We are launching, think of this as a new open source project for an open standard interface for a memory fabric, a coherent memory interface memory fabric. Now I'm going to spend a little bit of extra time than I had planned here because when we did do some of the preview for this, with, like I said, some of the press and industry analysts, some of the questions that started coming up was, well, what about Gen Z? What about CCIX? What about OpenCAPI? Oh my God, are you just throwing another one into the mix? So I thought, oh, okay, all right. Got to answer some of these questions. So let me walk you through this. When we started to think about the fact that we wanted, first of all, an open memory fabric. So a fabric being that everything can connect to, you need a switch to have a fabric. We needed something that was coherent, and we wanted it something that was on an open PHY, and an easy to use, readily available PHY. Well, when you kind of go through the options I just listed, so for example, CCIX and OpenCAPI are point-to-point protocols. They're not a fabric protocol. So couldn't use that. And so then when we looked at Gen Z, all open, all good. We love Gen Z. By the way, we love all these things, right? So just part of the reason I'm going through this is because I want to make sure you understand we're not doing this instead of or against or competing with. We love all these things. Everything has their purpose. But Gen Z didn't have a readily available PHY for us to use and didn't readily have a coherency framework for us to use. So when we put, that comparison chart through, and we wanted something that we could implement this coming year, there was nothing out there we could use. So then we said, look, we're going to take this open source ethos to heart, and we're actually going to tell the world what we're doing. We're going to publish it out there, and we're going to invite the world to come and play. And so we called it OmniExtend, and it is basically an open source coherency fabric. So for those of you who are new to coherency, just very quickly, coherency is what allows two or more processors, so it can be many, 2 or more processors, to in effect share memory resources so that it all looks like it's one big memory pool. And this is referred to as a cache coherency mechanism, and it's what makes sure that all of the caches in all of the various processors that you put in your fabric are all consistent. All right, so that's your quick 5-second tutorial on cache coherency. We're not doing this alone, and we invite others to play. So we're getting a fantastic contribution from Sci5 in the form of Tilelink. And so Sci5 has agreed to take Tilelink and extend it so that we can go beyond the processor. So today, Sci5 uses Tilelink as the coherency protocol inside the chip. So we're actually starting with that and extending it beyond the chip. And so then after that, in order to be a fabric, we're going to need a switch. And so our contribution is going to be all of the P4 source code for the switch, which will run on a Barefoot Networks Tofino switch processor. And your PHY will be a readily available Ethernet PHY. We will switch through that. So this will occur in sequence. The first thing you're going to be able to download is the core specification. We're getting very close to having the RISC-V Tilelink extension for over Ethernet. And then by, I'll call it April to June next year, that's sort of the plan, we will essentially contribute the P4 source code to the Barefoot Tofino. And so what that means is that anybody in a completely open and for a very low-cost way will be able to build a large cache-coherent machine using RISC-V processors. So that is announcement number one, and we're encouraging you to come and join and extend the RISC-V ecosystem by having an open cache-coherent memory fabric. Thank you. I have an ego, people. I need the applause. No, I'm just kidding. All right, you ready for number two? So last year, as I said, we were going to, we announced that we were going to transition 1 billion cores a year over to RISC-V, and we expect to double that, and we're going to transition all of our products. So what we've been busy doing over the past year is we have a team of folks who have developed Western Digital's first RISC-V core. So it's a 32-bit, two-way superscalar, in-order, 9-stage pipeline core. This is what I'll call a production-level core. And the reason why I call it that is because this is not an experiment. This is not a science fair project. This is the core that will be integrated into our first devices using RISC-V. At 28 nanometers up to 1.8 gigahertz, we're going to use it at a much lower performance than that, but if you want to push it, you can. We developed a programmable interrupt controller so you can have up to 255 interrupts, and we provided some industry standard bus access, and we also have debug support right on the chip. And we call our new core Swerve. So the RV, thank you. See? Good. So the RV, obviously, I'm going to go backwards here. So obviously, RV means RISC-V. So hopefully everybody got that pretty quick. So that's the significance to RV. The WE in the middle has two significance. One is Western Digital, so the WE in Western Digital. But the other is about collaboration and inclusiveness. It's about we, it's about us, it's about everybody collaborating together. And S, or Swerve, is about swerving around general purpose architectures for the special purpose. We are not trying to do any kind of head-on collision with the available general purpose processors. And so that's how the name Swerve came about. So this is Western Digital's RISC-V core. Now, a lot of people kind of go, okay, what kind of performance can we expect? So what we did is we dug out this paper that Krista and Dave Patterson and others did around 2015, I think. And the reason why we use this is because it was in one paper we were able to quote a whole bunch of CoreMark performance references. Now, go on the internet, you can find all sorts of other CoreMark numbers, find the one you prefer, it's all good. But this was just a really simple, easy way for us to reference one paper with a whole bunch of CoreMark numbers. Swerve sits at a 4.9, and it is an in-order core, as I said. So we think that for a first shot and a first core, we're delivering a core that's actually quite capable relative especially to everything that's out there, and as I said, a production level core. Now, we said we would use these cores, would be for our embedded, and it would be for internal uses. But on top of that, it's going to be completely open source. So the core is written using System Verilog. You'll be able to download it, use the RTL, play with it, find any issues with it, more eyeballs the better. You can use it in an unrestricted way, knock yourself out. And we will do our very best to provide everything you need to be successful with that core. Now, one of the areas where we're a little bit restricted is around the test bench support. because we're using a lot of proprietary IPs from commercial vendors. So we will provide some open source test bench support, excuse me. But if you are a commercial entity and you're using commercial tools, we'll try to give you a recipe of the commercial IP that you need. And then we should be able to provide you that, as under NDA, so that you can have access to the full. So it's not that we're trying to hold anything back, but we do respect people's intellectual property, and so we're not going to release IP that we don't own. And so but we are ready to make that available. And starting in Q1 2019, you'll have that access. So right now we're going through that to make sure we're all sort of very clean of any IP. We also had to do all the naming stuff around Swerve, all of those things. So the team is still working on that. And if you recall a couple of slides ago, I did say it was verilator clean. That's why that's significant, because we expect people in the open source community to use that as an RTL simulator and be able to verify the core. So we're obviously pretty excited about this. We hope that people will download it, use it, etc. One part, actually, I would love to get feedback from all of you. Send me an email if you want to, martin.fink@wdc.com. We have heard that there might be some interest in having, we'll call it a Western Digital certified version of the core, right? Because if you take the core, start using it, no restrictions. It's Apache license, knock yourself out. But that some people might want to have this sort of official Swerve branded version of the core. And so we've started sort of an internal investigation on should we provide that. And so if this is something that would be of interest to you, we'd love to just get some feedback from you that you'd like to get that from us, and we'll go work on that. All right, so the next one is we also built an instruction set simulator, and it too will be fully open source. So independent of the RTL for Swerve, we had a separate team that has been working on a RISC-V instruction set simulator. And we did that as, again, completely separate from the RTL team so that we could ensure that what we were building was conformant to the RISC-V specification. And so this instruction set simulator will be available for anyone to use. You can use it to continue to do validation work on the Swerve core. If you're building your own core and you want an instruction set simulator to validate your core, you'll be able to do that because it's essentially set up to provide full test bench support. So you basically connect your core through RTL, provide the test bench, and you'll be able to do instruction validation on an instruction by instruction basis. And we've run our own core at the rate of billions of instructions successfully through the simulator. In the early days, if there was challenges between the RTL and the simulator, we had to go through a detailed investigation as to whether the RTL or the simulator had issues, and so we worked through all of that. And so this, again, will be available for anyone to use, enhance, improve, provide more capabilities, etc. And I believe that one is available for download now. Okay? All right, so that's it. We had 3 announcements. OmniExtend Open Memory Fabric. By the way, you should be able to go to our booth and see it in action. Not the fabric, but the point-to-point. So you should be able to see the OmniExtend memory protocol working point-to-point in our booth if you go to that later today. So we're really excited about that. But again, based on ubiquitous Ethernet, and so you'll be able to use a very low-cost ubiquitous PHY with the protocol. We have our Swerve core, again, as we're using internally, production level core, system Verilog, Verilator clean, lots of capabilities, and that too will be open source. And we hope that people will take a look, provide feedback. If you find issues, obviously we want to know, but we think you'll like what you see. Then finally, the instruction set simulator that we built alongside Swerve, but independent of Swerve, and that is available today. And so come help us with OmniExtend. It's in the very, very early stages. Download the spec and then give us some feedback and tell us how we should move forward. And then for Swerve and ISS, again, download, use, extend, wrap tools around it, do whatever you want to go do, and we'll help you do that. So all of this is motivated by the need for us to have open standard interfaces and drive this next generation where data is at the center of the universe, not the processor, and that we enable people to build special purpose architectures in order to drive those next generation architectures. And please go spend time at the booth. Go see Ivan on Platform I/O if you want to see how I do my coding on the weekend, and we'll get you set up with RISC-V assembly language support. So thank you very much for taking the time and showing up today. Love to see the ecosystem growth. Have a great day.